Hello everyone, welcome to my CCI Enterprise course. In this course, you will learn all the technology related to your CCI Enterprise journey. And in case if you are looking for the actual lab type of scenario and the solution, then you can reach out. You can send me email ratnesh721kumar721 that is here, and then I will send you that detailed info that how my students they are preparing for their actual lab training. It will be almost similar that what you will expect in the exam. You can practice. I will help you. I will guide you for 1 month to clear this exam. I will help you step by step how to drill down um, the solution, drill down the technology into small pieces, and I will help you to pass your exam in first attempt. So go for this course. This will be a good place where you can learn the technology. But if you are serious about the CCI lab exam, then you can drop me an email and you can get the detailed info. All right, so let me stop this video, and if you watch this video, you can simply contact me and you can get the information related to the new update that we have in the CCI Enterprise Lab. Let us understand the routing fundamental. In this case, we are going to understand about EIGRP basics. Now, what is happening that all the routing protocols, they have same type of fundamental. That means that they have to establish the communication. So suppose if two routers are there, obviously they will form some sort of relationship in between them over the reliable transport, and then only they will start exchanging their routing informations. Correct. So in the same line, you'll find that they have to establish a communication. Then they will start exchanging the routes. They have to perform the competition. That means suppose if you have multiple nodes in between and you're exchanging the routes, that means they have to use their algorithm to get the best route, to select the best path and all those calculations. Correct. In EIGRP, we have something called dual algorithm. In OSPF, we have a SPF algorithm. We'll check dual algorithm in upcoming slides more about that. But yeah, to build the relationship, to exchange the route, to perform the computation, and finally, you install the route inside the memory. So that should be consistent. That means whenever your traffic want to reach that, you can use your memory, your CPU will tell you, okay, you can go by this. So all the time you will actually not build the same thing. You will use whatever cached inside and then perform the routing. Great. So you can see the fundamentals are there, and EIGRP is no exception. EIGRP is using some sort of reliable transport RTP to build the relationship in between that. They have the reliable transport. Again, they are doing some sort of three-way handshaking. First of all, to build the relationship. So this was the point one. Then a reliable transport to route exchange. Then path competition. We have dual algorithm, diffuse and update algorithm. Then finally, they have the routing table update and peer update if it is required. Correct. But yeah, if you go and sequence, you'll find that most of the protocol having the same type of strategy. We know that EIGRP is a distance vector routing protocol. Sometimes we are referring that this is advanced distance routing protocol because it has the attribute of distance vector protocol, but it has attribute taken from the link state type of protocols as well. Now, how distance vector protocol they are working? So they know the prefix and the next hop. So suppose if D has to learn the A prefix, so obviously they will learn via B and C. So D can learn 10110 either from B or C. Correct. That means that to reach here, it has to go here and it has to go here. It's just straightforward. So B and C, first of all, they will learn the 10110, and then D will learn from either from B or C. It depends that whatever matic is better, one will be preferred, other will be backup. Now we'll see the problem here. So problem here is this, and that's a very important point. Now, when we are talking about the routing protocol, more precisely the distance vector routing protocols, so we do not have a visibility of the topology. So the devices in between, they do not have a visibility of entire database. So suppose if is one of the router, he don't know the, means he don't have the visibility what is there, correct? So something is happening in between A and B, and if don't know, suppose if has to go and learn 10.1.1.0, so it will be difficult for him to know him what is happening behind the scene, because topology you can see is hidden, and that's the problem, and that's the overcome. We'll see that how EIGRP is coming out of this. Now with this problem, what is happening, that when A and B, suppose if this link will fail, so D will send, so D will tell, hey, see, this 10.1.1.0, because some link issue is there, I'm not able to send you. Then what F will do, it will start sending query to everyone, all his neighbors. See, do you have this network, do you have this network, do you have network? And doing so, this will result in increase in CPU, memory, and convergence time, correct? Now this is the problem, because we don't have full visibility in the topology, and that's actually the problem with the distance vector protocols. Later on, we will discuss about uh, terms that how we can go and overcome from these issues, and how we can limit on these criterias. Still, we are in the basics of EIGRP, and we are going to learn more terms and features inside EIGRP. One of the terms we have in EIGRP is that they are part of autonomous system. So autonomous system is what? Autonomous system is that you are under same administrative control, you are under same number. So you should have a consistent routing policy, and then um, you're part of one system, you're part of one tag, like that you can think. So autonomous system 100 belongs to me, it's my domain, it's my area. So a part of same group, that means the autonomous system. Let me quickly summarize whatever we have studied earlier in coming 2 slides. EIGRP is using diffusion update algorithm, okay, to do the computation, compute. So compute part is happening with respect to dual algorithm. They are part of same autonomous system, that means same administrative control, same policy segment, etc. So this and this very important point. Then EIGRP can use unicast, or they can use multicast to send the hello packet, correct? They are using RTP to build the trust communication in between two nodes. Now, EIGRP, to build their routing database, do not send periodic full table routing update. Update are sent when a change occurs. Okay, so that's very important. It's like RIP, they are not sending the entire databases all the time. If there is any change, then they are sending the update, and they are classless protocol. They are supporting a variable length subnet mask. So these are very important high points related to EIGRP. They are multicast, they are multi-protocol support, means they are supporting different type of routed protocol stack like IP, IPX, AppleTalk, etc. The internal AD is 90, the external AD is 170. Their metric, although this EIGRP metric value is little bit complex to understand. They depend upon 5 criterias: bandwidth, delay, reliability, load, and MTU. Some of the books, they are referring that MTU is not part of metric value, but you can think that at this point of time, you can think that, okay, EIGRP metric value heavily relying upon bandwidth and the delay. Okay, reliability and load, they have less impact, but mostly they are depending upon bandwidth and the delay. They can go up to the maximum hop count of 224, and default hop count will be 100. And finally, while they are building their routing table, their best table, So first of all, they are also going into the phases, like they are building the neighbor table, topology table, and then finally the routing table. Remember, the topology table, a list of all the routes in same administrative control or same administrative policy, same AS. Like this AS is not like BGP AS, but they are part of same autonomous system. Great. So these are the basic point related to EIGRP. Let's stop here. In this section, we will go and check the basic configuration related to EIGRP. That means that when we log into the router and when we are doing the day zero type of configuration, the first configuration what we want to do related to EIGRP. Now, EIGRP, Cisco has done some enhancement. So initially EIGRP having the classical mode, that means you can go log into the router, go to the configuration mode, and you can write router EIGRP and then the AS name, AS system name, like 10, 20, 30, etc. So router EIGRP and then 10. That means you are kicking EIGRP process start. So EIGRP route process will start with this command. And then later on, we can go and add commands related to network advertisements and some other. Correct. So that is one of the mode that is called termed as a classical mode. But Cisco has done the enhancement, and now we have advanced mode. You can think as well, advanced in terms of named EIGRP mode as well. Now, named EIGRP mode, that means if we are supporting or if we are running the address based or the name based EIGRP, more precisely, it is termed as that. So in that case, we have multiple address family support plus some other added features as well. So here you can see side by side the differences in terms of configuration. The classical EIGRP, normally we can go router EIGRP1, we can give the network command, summary command, etc. And then we can go to the interfaces, and over the interfaces, we can go and run the summary address EIGRP command. Okay, but when we are coming to the name base, then we can go to the EIGRP, we can give the name. Okay? And this name is not something that should be common in all the routers. It is something like you are starting the name based EIGRP, and then inside that you can go, still you have to go and give the autonomous system. So name is not something that we should have same in all the routers. It's not a constant thing. In router 1 I can give different name, router 2 I can give different name, router 3 I can give different name, but for the sake of uniformity, sake of simplicity, we can give same name within the autonomous system. Correct. So that's one thing. So here you can see that how it will be. You can go and give a router EIGRP and the name. Then we can go inside different type of address families like IPv4, IPv6, or certain VRFs as well. Once we are inside the address family, then we can go and run the classical EIGRP command. So here you can see that we can go to the address interface, address family interface, and give the summary address, one thing. Then the router based command or routing level command, we can go to topology base, and then we can do the summarization. We can change the K values related to metrics, and then we can go and give the network commands. Correct. So you can see that if we are using the named based EIGRP, so at that time, all the address families that can be put inside same, like IPv4, IPv6, VRFs, etc. Everything is supported under one name, under one hierarchy. Means obviously you have to go inside the address family and you have to write the command related to IPv4, IPv6, etc. But it is uniform now. It is clubbed in an organized way. Unlike classical EIGRP, it will work, do the same thing, but again, for different address families, you have to go and write it separately. Correct. So now when we are talking about the EIGRP, the configuration is straightforward, but when we are running with the named mode, they are going to support IPv4, IPv6, VRF instances as well, and we have a uniform type of configuration throughout the configuration or throughout the system. Correct. So you can go to the name, then you can go to the address family, VRF, even multi VRF supports are there, multiple address family supports are also there. Apart from that, there is name-based EIGRP. They are supporting multiple interfaces as well. So you can see that you may have default interface, or you can go to the specific interface and you can execute the command. Like you can see here that we can go to one of the AF interface and then we can do the summary. Okay. And then finally, you can see this is the summary that we have. So you can go to IPv4, IPv6 address family. So once we are inside the named, we can go to the address family IPv4. We can give the summary command related to network. We can go to IPv4 VRF. Then we can go and use network command. We can go to the IPv6 and then we can give the IPv6 related commands. Then we can go inside IPv6 VRF and then we can go and give the commands. Correct. So you can see that in wider picture, in longer run, the usability that we have with respect to named based EIGRP. In this section, we'll learn that how EIGRP, they are going to form the neighbor relationship. Now, EIGRP, they are using multicast packet 224.0.0.10 to exchange their hello packets. They can use a unicast packets as well to do so. Now, while forming the neighbor relationship, node A and B, they are using some sort of three-way handshaking or three-way communication to form the neighbor relationship. So how it is working? First of all, suppose if B has sent the hello packet to A, then A will go and send the init packet to B, some packet with null bit inside that. And meanwhile, what it will do, it will mark the state as a pending. So pending in terms of that, the neighbor relationship is pending, it is in progress. Correct. Now, once A will send the init bit to B, then B has to send the ACK back, and this is the third step. So step number one is the hello. Step number two is the init exchange. That means A has to send the init to B. And step number three, that B has to send the ACK for A init. So that means that three-way handshake process will complete, and now A will mark that pending state to the up state. So that means now A and B, they are neighbors, and then they are ready to exchange further routing informations. Correct. To verify the neighbor is up or down, we have one CLI command, show IP EIGRP neighbors. Now with this command, we are going to get good amount of information about the neighbor. First of all, the order in which I have learned the neighbor, what are my neighbor addresses, which interfaces I am learning the neighbors, the hold down time. That means how much time I have to wait to mark that neighbor is down. Generally, this is 3 into hello time. So suppose if your hello time is 5 seconds, so this will be starting from 15, 14, 13 going to 1, 0. After 0, that means that neighbor is down. The neighbor is up from last 6 days or 2 weeks or 3 weeks, etc. Those timers, those time counters. Then we have SRTT, that is a smooth round trip timer, that is going to tell you that how long it will take for this neighbor to respond to the reliable packet. And again, here you can see that the description for SRTT, that average amount of time it takes to get an ACK for a reliable packet for his peer. Means you are waiting for your peer to get the acknowledgement. That's the average, A to B, B to E. That's the round trip timer. Then we have request timeout. Request timeout means how much time you will wait for the retransmission related to acknowledgement. Queue count is there. Queue count is going to tell you that if any packets they are stuck. If queue count, if you get some numbers here, that means some issues, some problem with the line, link, etc. Finally, the sequence number. There's the last reliable packet sent. Great. So good amount of information we are getting. Still in that, if we go and use the keyword detail, so we are going to get some more information. So we are going to get the number of retransmissions and retries, the version of iOS and EIGRP. So you can see that the versions of iOS, EIGRP, retransmit, retrans, and if we have any stub configuration. So we are going to get these details inside show IP EIGRP neighbor detail. Some other informations as well. So suppose A and B, they have formed the neighbor relationship with a default hello timer of 5 seconds. But in case if you want to change the timer, so we have option. We can go to the link basis and we can change the timer. So we can go and use the command IP hello interval EIGRP. EIGRP 10. 10 is the autonomous system. And then we can go and use the 7 second. 7 second means this, now the timer for hello packet is 7 seconds instead of default 5 second. Likewise, we can go and change the hold down timer as well. So instead of 15 second, if you want to make 15 second, if you want to make 21 second, you can do it. Now suppose one device having a timer 5 and 15 second, other device has timer 10 and 30 second, still they will form the relationship. The way that they are transmitting their hello or dead timers, those timers will get changed. Okay. Now one very important point here is this, that while forming the neighbor relationship, these devices, they should use their primary addresses, and their primary addresses should be part of same subnet. Suppose if they are not part of same subnet, then you will get one error message that EIGRP neighbor not in the common subnet. Okay. And finally, if you want to log the changes, so we have the CLI command we can go and use. First of all, go to the routing process and use EIGRP log neighbor changes, and then you can use EIGRP log neighbor warning. Okay, let's stop here. In this section, we are going to understand about EIGRP packet types and different type of flags that EIGRP is using. Now we know that EIGRP, first of all, they are building the relationship, neighbor relationship in between the nodes. So suppose if you are in the shared media point-to-point link or NBMA network, any type of network or media we have, EIGRP will go, first of all, they will build the neighbor relationship and then they will exchange the packets. Now, that's interesting fact here about EIGRP is that they are using both type of messages. So they are using unreliable messages or the packet types, and they are using reliable messages or packet types as well. Now, while building the neighbor relationship, when they are going with three-way handshaking, means you're sending the hello, receiving the init or initialization bit, then you're sending the ACK, correct? So that three-way handshaking process that EIGRP has, after that, so during that, they are using unreliable messages like they are using hellos. So hellos and ACK, they are part of unreliable message exchange. But after that, whenever they will go and do the query, reply, update, etc., means those type of messages types, they are falling under reliable criteria. So here you can see that the reliable are hellos and acknowledgement, and then update, queries, replies, stuck in active queries and replies, they're part of a reliable packet exchange. Now, why we are talking about reliable or unreliable? Because if it is reliable, that means you are using some sort of sequence number, you are using some sort of ACK packets, acknowledgement. Correct? We know this thing from the TCP world that they are using connection-oriented, reliable communication, that TCP protocol. Like that, the EIGRP, they are using RTP, and the major packet types you can see here that hello, query, reply, request, and update. The hello and ACK, they are falling under unreliable packet exchange, but the rest of them are reliable. Means they have the sequence number and the acknowledgement. Let me quickly go one by one. So hellos and ACK, we know that hellos, when they try to form the neighbor relationship, the EIGRP, when they are discovering some new neighbors, then at that time they are using hellos and ACK. Update means that you want to update, means you learn something and you want to share that information to your neighbors. So that is the update. Then query, suppose if your neighbor or someone is looking for new messages, new network actually, or new subnets, then they can send query packet and then query. So if someone will do query, so the reply will come into the picture. correct? Now these update, query, reply, stuck inactive, query, reply, all these packages, they should have the acknowledgement because they are falling under reliable packet criterias. Then finally, you have a stuck inactive. That means that suppose you don't know the network, you are doing the query, but still you are not getting the reply. So at that time, SIE query, so stuck inactive query, so they will go and do the query to the non-replying peers. So that means your query is forwarded throughout the network to until unless you'll get the response. Okay. Now we have very important flags as well. So one of the flag we know from the previous section, that is the init bit. During the hello exchange, it is going to be used. Apart from that, we have CR, something known as conditionally received. We are going to discuss about CR in upcoming slide. We have RS, that is the restart flag, and this is set in case of hellos and init update, and when we are using non-stop forwarding signaling. So again, at the time of initial negotiation, this RS restart flag will come into the picture, but in case of non-stop forwarding NSF signaling. Then we have EOT, end of table. What is the usability of this? Again, I will cover this in the upcoming slide. So these 2 points I want to cover in detail in the upcoming slide, the CR and the EOT, because these are important. Great. So before reaching to CR and EOT, we have some a few more slides for information purpose. Let's talk about updates and advertisement. We know that whatever network that router A has, he wants to send the update. Obviously, he wants to advertise their own network to the neighbor. Now, what will happen when A will send the update to B? B will send a poison reserve. Okay, so what does it mean? This poison reverse, that means that poison reverse route is something that, okay, I got the route from yourself. Now you will not get the same route from myself. So in other words, this poison reverse means that do not teach me what I am teaching you. Like that is root poisoning type of thing. Correct? All right. So that is one very important thing. So what is happening here, that A is sending the update to B, then B, what they are doing, they are using this poison reverse route. So B in the update, what they are doing, that they are making the matic as a infinity. Obviously, this is something that A has learned. I learned from A, I don't want to teach you A. That's the indirect meaning. Then finally, what is happening, that the A, and this we have discussed here, means we have talked about this EOT, end of table. So now A, what the A is doing, when he is finishing sending all the update from himself to router number B, they are sending the marker, the flag EOT, end of table. That means that whatever I have explained to you. Now I don't have anything. That's the marker. So A is putting the marker. That's a flag actually. EOT, end of table. Okay. So that's the use of EOT. Correct. You're telling your neighbor, your peer, that see, finished. Everything I have told to you, now it finished. My table is finished. So that's EOT. So now we know init flag, we know about EOT, we know about RS. I'll go and cover CR as well, conditional receive. This is also very important. Great. So we know at this point of time that apart from acknowledgement, apart from hello packets, you are getting the acknowledgement for everything. Correct? All the packet, all the message exchange we are getting. Now we have very important flag here termed as a conditional receive. What is happening in conditional receive is that suppose A is sending update to B, C, and D. So after sending the update, obviously A is looking for acknowledgement. Now, due to some reason, if A is getting the acknowledgement from C and D, but it is not getting the acknowledgement from B, that means that A will go and start the conditional receive mode. Okay, so that means here the conditional receive mode will get enabled before the timer will get expire, and A will go and send the retransmit bit. The CR mode will be act. So CR mode is enabled. Now what the CR mode will do, let's understand about that. But meanwhile, since A hasn't got the acknowledgement, so next time when it will build its hello packet, what A will do, in that hello packet, he will mention the B's address as well. Now, when this particular packet will be multicast in a network, so C and D will receive this message and it will open that hello packet. It will see, oh, this message having some other address. This message does not include my address. So C will think this message does not have my address. D will think this message does not have my address. That means that we will also put ourselves into CR mode. Okay, so remember, whoever address is there in this built hello packet, that particular device will not go into CR mode. So for that particular device, CR bit or flag is not active. So here it is active. Suppose 1 means active. Here it is active. 1 means active. At the moment, we'll think like that. 1 is active, and here CR mode is 0. So that means now since A, C, and D, they are part of CR, conditional receive. So that means they will go and they can exchange any type of reliable packet. Okay, update, query, whatever. They will do the exchange. But since B is still the CR is not activated for B, that means still A will try to establish the neighbor relationship with the unreliable packet exchange. And once this will be completed, then only now you can think that now you can think like B will also become CR. So for B also CR will become 1. And if all the devices having CR bit flag 1, that means they are eligible to do the reliable packet exchange. So now you can understand this concept of reliability and unreliability. Up to what point EIGRP is using unreliable packet exchange, and then after up to what point EIGRP using the reliable packet exchange. All right, so let's just stop here. Let us learn about EIGRP metric. EIGRP metric formula is a little bit complex, and I'm going to show you that how it look like and how we can do the basic calculation from there. In the next section, we have EIGRP basic lab. There also you will find that how you can calculate the EIGRP formula, means from that formula how you can derive the metric value. Okay, so here you can see that EIGRP, inside EIGRP, we know that the metric is there. All the routing protocols, they have the metric. According to that, they are selecting or get selected for the best path. In EIGRP, we have different values such as load, reliability, MTU. You can see internal tag as well. I will show that where it will be used. Apart from that, we have the bandwidth and delay. So 5 values are there, and those values are associated with some constants, some K values as well. Okay, so delay is something, it's a cumulative delay. Next slide, I'll show that how it can get calculated. Bandwidth is used as a minimum bandwidth over the link. Then MTU, basically MTU is not used. So some places you'll find that MTU being used inside EIGRP metric calculation. Some places you'll find that it is not being used. Mainly delay bandwidth is used heavily, but if you want to tune, you can go and use other factors as well, such as reliability and load. Reliability means if the value is 255, that means it's 100% reliable. In case of load, its value is 255, that is 100% load is there, that is not good. So if load is less, that means it's good for the link, it's good for the routes to learn via that path. And then you can see one new item here, that's the internal tag. A tag assigned by the network administrator that is untouched by EIGRP, means that is assigned by network engineer. Here you can see the formula. You have router A, B, and C. And now it's easy to understand when we are talking only in terms of bandwidth and delay. Okay, so bandwidth, you can see the bandwidth here. Three places you can see bandwidth 1156. And as for the formula, we know that the metric value is 10 to power 7 divided by bandwidth in kbps, and that will be the minimum bandwidth. So suppose 56 kbps, if it is minimum out of 3, so that will be taken, correct? And then we have delay in terms of cumulative delay in terms of microseconds, correct? So delay, you can see that delay will get added. So here it will be 100, then in this hop the delay is 1100, this hop the delay is 3100, so delay will be 3100, and it is in 10 of minus 3. It's 10 of it's actually in microseconds, and then it will get multiplied by 256, and whatever value will come, that will be the metric value. Now in the lab section, you'll see the actual mathematical formula, the calculation. I will open the calculator and I'll show you that. Great. So what's the big formula? We don't need to memorize this formula. Here you can see that the metric value, and again with respect to classical metric value. Classical means when we are running the classical EIGRP, we know that we have two modes. We have classical, correct, and we have named mode as well. In case of named mode, you'll find that things will be different. The metric, even the metric formula is more complex there. So here, what is happening that K1, the constant K1 and constant K3 become 1. So your bandwidth value, and you'll find your delay value will become 1. But rest of the things like K2, K4, K5 related to load, reliability, MTU, those will become 0. So finally, the formula will come little bit like this: metric equal to 10 power 7 by bandwidth in kbps into plus cumulative delay in terms of microseconds, 10 of minus 3, and then into 256. Again, this is a classic metric formula, but when we are using the named based EIGRP, the formula got changed. So here you can see with respect to name based EIGRP, the formula here you have one more constant K6, and that is there related to extended metric. So now here you can see this is a big formula, K into throughput, then K2 into throughput divided by 256 minus load, K3 latency, K6 into extended metrics into K5 divided by K4 plus 11. It's a big formula, correct? But here also, if you go and make the constant as a 0, so suppose if you go and make K2, K4, K5, K6 as 0, so again you are calculating the formula upon bandwidth. Bandwidth is actually the throughput. So you are calculating over throughput and you are calculating over latency. So the final formula will be depending upon the throughput, and again how the name-based EIGRP, they are calculating the throughput. There are measures, methods to check the throughput, like the max throughput or net throughput, etc. So throughput and then the latency, depending upon that. And here you can see little bit of description. So the latency derived from the interface delay, throughput derived from the interface bandwidth. See, in the classical, here also in the classical EIGRP also you can see that we have the delay factor, correct? And delay is latency factor here in name based EIGRP metric formula. In classical also you have bandwidth. Here in the name based metric, you'll find that throughput is derived from the bandwidth, and then the load over the interface, reliability over the interface, extended metric, that is derived from the router or the configuration. All right, so these are the formula, these are the calculations related to the EIGRP metric. Next section, we are going to perform a lab task. In that lab, we are going to learn about the classical metric formula only. But if you are much more interested about the new metric calculations and formula, you can refer some of the Cisco websites. Let us do the EIGRP configuration And after that configuration, I will go and verify first of all the basic things like how EIGRP having their neighbor table, then their topology table and their routing table. Plus we'll see the various type of packet types that they have. Then we'll go and check the other things that we have studied in the previous section. So let's start. And what I'm going to do, you can see here the diagram R1 and switch 105. So in between that, you can see the interfaces. I'm going to assign the IP address to all these related interfaces, and plus I'm going to give one loopback address as well, just for verification purpose or testing purpose. So let me quickly go and assign the IP addresses to all these interfaces. So I have assigned the IP addresses to all the interfaces. Let me quickly show you that. We can go and verify once. Show IP interface brief, and I want to include the manual. We'll go and run this to all these devices 101, 102, 103, 5 and R1, and I should press enter, send the script. So here you can see that over R1 I have this IP address, then switch number 105 I have these IP addresses. Although I haven't pinged and verified that they are reachable or not, but I have assigned the IP addresses over the interfaces and created over the loopback interface as well as per our topology. Okay, so next task I have that I should run EIGRP. So let's go and enable the router. EIGRP, we know that we have to give the autonomous system for that. So let me show you from here, from the global config mode, router EIGRP, and then we can assign the autonomous system. For example, I'm using 10. I'm going to use no auto summary, means I don't want to do the automatic summary. So that's why this no auto summary command. Then I want to advertise the network. Now we know that what type of IP we have, and if you want to check the network, connected network, you can go and run do show IP route or show IP route, so you can get the connected network list. But because I have this network here, so I can go and use, and then we have this option that we can use the wildcard bit. Then I can go and use the other network. Oops. Then I have other network as well, that is this one, and I can go and use the wildcard bit here as well, then the third and the fourth one. So this is my third network, and then finally the fourth one. The loopback address having /32, the CIDR, so I will go and use this 00000 as a wildcard bit. We can quickly check the EIGRP configuration. So here you can see that we have these many network. Now I should go and enable this to the other devices as well. So we have done the configuration to 101. Let me go and do it to 103. So for 103 the network is, so let's go to 103 router EIGRP 10. We should have the same autonomous system, no auto summary. Then the network, we know that network is this. At the moment I enable or I run this command, you'll see that they will start forming the neighbor table, topology table, and the final is the routing table. So dual dual algorithm will run here. Here you can see that it is running the dual algorithm, and then we have the routing table as well. All right, so at this point of time, at least I can go and check show IP EIGRP. First of all, the neighbor table. So here you can see that this guy is the neighbor, the uptime is this many second. Rest of the things, we don't have much worry. We don't need to worry about this request timeout, the queue count, sequence number, a round trip timer, etc. If you have any issue at that time, you'll see that queue count is increasing, or you have the RTO value is increasing, or uh, round trip timer is increasing, etc. Okay. So first table will be the neighbor table. Then you can go and check the other stuffs as well. Like I can go and check show IP, EIGRP, topology table. That's the database you have. Now here you can see that you have the successor, feasible distance successors, and then you can see that you have the metric value as well. So here you can see your FT values. Now this calculation, we'll discuss this in upcoming slides, or even now also we can discuss. So I need to open the mathematical calculation and the calculator. So for that, we'll go and check what's the bandwidth and how this calculation is coming into the picture. That's 409600. Okay, that's the FT. Again, you can see that P stands for passive, and then you have all the codes. So let me quickly open the calculator and let's do the calculation here. So we know roughly the formula for the metric value is, the metric value is 256 into 7 divided by bandwidth in kbps and plus delay. Roughly, this is the rough calculation. So let's try to understand first of all the bandwidth for the interface. Everywhere we are using Mbps, so my bandwidth is 100 Mbps. Now this 100 Mbps, let's calculate it in kbps. So let's try to do this. Now 10 to the power 7, so 4, 5, 6, 7 divided by 100 Mbps means 100 into 1000, means we have to convert into kbps. So number of zeros will be 0, that is 100, and then 30, so that will become the kbps. So the final value will be 100 and plus delay. So I should go and check the delay over the interface. So for example, show interface E0/0. Now if you go here and you can see the delay, this is in microsecond, this is not in this is, yeah, 10 to the power minus 6, that's the microsecond we have, and that's okay. So what will be the value for this? 1000 into 10 to the minus 6, correct? Okay, and that's correct format actually. So let's see. Let me open the calculator one more time. So that means we should go and add 1000 here, and then if we do 256, 281600, I can see the bandwidth in kilobits, that is showing 10 to the power 4 only. And let's go and verify that what is our metric value. That is 281600, that's correct. So yep, let me open the calculator, and here you can see you have the exact 281600. Yeah, so this is the way that we can do the calculation for the metric. Okay, so what I'm going to do here now, let's just stop here, and this lab we will study some theory, and again I'm going to build, and I'll going to continuously build this lab as well in the upcoming sections as well. In this section, we are going to learn about EIGRP topology table, and in the next section, we'll discuss about the dual algorithm. Now, to understand the EIGRP topology table is a key, because mostly you'll find that EIGRP having issues, and if they have issues, we should understand that how its database construct, how the topology table built is there, because we know that there are three stages: neighbor table, so we can go and do the troubleshooting related to neighbor table. Then on basis of neighbor table, we have topology table. That's actually the core local database that we have inside EIGRP. And if we are able to figure out that what is the issue inside the topology table, some of the routes are missing, some of the links are missing, then we can easily figure out, we can easily do the troubleshooting related to EIGRP. Okay, so what this topology table consists of? It consists of all known paths, local learn, and the external routes. That is coming via the redistribution. And once we have the topology table, so topology table will present it for dual algorithm, and after that dual algorithm will run, and then we'll go get the best path. Dual algorithm we are going to discuss in the next section. All right. So we know the steps. We know the steps are neighbor table, then topology table, and then finally we have the best path. That's the routing table. What are the key terms we have inside topology table? How we can go and understand, memorize those key terms that I'm going to explain here. Now, this diagram seems very easy, and we can refer this diagram. For example, if you are going for your CCNP exams, this is actually key. They may test you upon various key terms and the usability. So you may get terms such as what is reported distance, what is compute distance, what's the feasible distance, what's the successor, feasible successor, etc. There are so many interrelated terms that we should understand. Okay, so now let's understand all these terms one by one. First of all, suppose A is the source, and for A, if the destination is E, so behind E, suppose I have some destination route that want to reach to A, correct? So let's try to understand the common terminologies used inside EIGRP. So first term is the reported distance. Now reported distance, so A has their neighbors, correct? B, C, and D. B, C, and D are the neighbors of A. So that means that whatever routes you have, actually these are the metric, but this is in simplified manner. So whatever the route metric we have, so metrics such as B to E is 10, C to E is 10, and then D to E is 30. So these metric value that is coming from the upstream routers such as B, C, D, they are termed as a reported distance. So 10, 10, 30, they are the reported distance. Clear? So whatever I'm learning, whatever metric I'm learning from my neighbor, those are reported to me. Those are the reported distance. Okay, straightforward. Now then, what is the compute distance? Compute distance, you can see here the definition. Now these things are linked. So compute distance is reported distance plus the link cost. So you have reported distance 10, 10, and 30, and then the compute distance here, it will be 10 plus 10. Here it will be 15 plus 10. Here it will be 15 plus 30. So that means for three different link, you can see that you have three different links, so three different compute distance. These are the metric compute distance. So now once we understand the reported distance, once we understand the compute distance, understanding of feasible distance is easy. So feasible distance, there is one mathematical formula, feasible distance equal to lower of compute distance. Now you have three compute distances here, such as 20, 25 and 45, correct? Now in these three, we know that 20 is less. So 20 will become the feasible distance. That means that this is, so feasible distance equal to least of the compute distance, and that will become the successor. Correct? So successor, now successor is your primary path that will be installed inside the routing table. But the key here inside EIGRP, that EIGRP, not only they have the successor, but they have the backup path as well. That's the feasible successor as well. Now there is condition. So there is feasible condition for feasible successor. And now the feasible condition is this mathematical formula. So if the reported distance will be less than the feasible distance, remember what is feasible distance? That is equal to list of compute distance. So that means indirectly, if reported distance is less than least of the compute distance, that will become the feasible successor or backup path. Okay, so in this case, you can see that what is the reported distance and what is the feasible. We know that the feasible distance we have is 20, correct? 20 is our feasible distance because 10 plus 10, this is my primary path. Okay, so my feasible distance, my primary path metric value, or my primary path distance or compute distance is 20, correct? Now here you can see that C to E, what is that? That is 10. So that means that 10 is less than 20, and that's why this particular link is the feasible successor. This particular link is the secondary path. Now there may be chances that it will take some time to understand the uh, reported distance, the compute distance, the feasible distance, the feasibility condition, the feasible successor, etc. So you please pause the recording here, go back, watch that 10-minute or maybe 6-7 minute video, come back here. You will understand each and everything I have explained here. And it's very important. Only with this diagram, we can understand each and everything related to topology table inside EIGRP. And this knowledge will be useful in the next section when we'll go and understand the dual algorithm. Okay, active and passive states are very easy. Passive means good, that means it is a stable state. Active means actively I'm looking for a stable routes, like that we can think. Okay, but the key here is these terms. They should understand these terms. Now once we understand these terms, then you can go and check inside your lab, inside your output. So you can go and check show EIGRP I address family IPv4 topology, or show IP EIGRP topology table, like that. And then we can go and mark that, okay, so my successor having the feasible distance, then you have the compute distance, and then you have the reported distance. Remember, feasible distance equal to least of compute distance, correct? CD. So that means there is direct proportionate relationship between feasible distance and compute distance. Okay, so that's why you can see that this feasible distance and this compute distance are same, because these are the minimum. And then you have the successor criteria as well. So we know that what is the feasible successor criteria, and you can see in the bottom, the feasible successor should be less than. So here you can see that the condition. So feasible successor condition itself is that RD, reported distance, should be less than the FT, feasible distance. Okay, so now we understand that the use of the topology table. Some other terms are there because topology table is very, very important, and topology table in EIGRP is quite proactive as well. So not only they have the primary path, but they have the secondary path as well. So that means if route will get converged, it will not reconverge the entire protocol, but it will check, oh, I have my backup path with me, I can go and check it. Now, EIGRP, not only that they have the backup path with them, but they have possible successors as well, like possible backups as well. And that's the key as explained here. So you can see here in this output that you have the feasible distance, you have the successor, you have the backup path. That's the feasible successor, correct? But EIGRP having possible successors as well. So that means that in case of outage, that entire EIGRP will not reconverge, because to do the reconvergence, again, all the routers, they will use their processing to compute, to compute the best path, to compute the metrics, etc. So it will take some convergence. Not only the convergence is not like it's taking some time, but your resources, they are getting utilized, your memory, process, etc. So to prevent from that, they have not only the feasible successor, the backup path, but they know that who can be their possible successors. Okay. Great. And finally, we can go and we can check certain outputs are there. For example, if you are looking for the detailed information about your destination, so you have the command show IP EIGRP topology, this destination. So this destination is learned via 3 different paths, and all these 3 different paths you can see here and their detail. Apart from that, if you have any external route, so you can see if I am learning external route injected in router D, so that external route information also we are getting with the topology command and with the destination external route IP and subnet. Great. So this was the explanation related to the EIGRP topology table. It's very important. Let's stop here. And next section we'll learn about the dual algorithm. In this important section, we are going to understand about behind the scene how this diffusion update algorithm work. We have the topology table. We know this thing that we have the topology table, and on top of topology table, so topology table as an input, then the dual algorithm will work, and how the dual algorithm will give loop-free best path, and how the convergence will be faster in case of EIGRP. So we are going to discuss about all these important points. Now let's try to understand via the diagram. We are going to do quick revision that what we have studied in the previous section. You can see here you have one node, N node, and for N node, different routers they want to reach. So for example, if A want to reach, so what will be the A feasible distance? So from A, obviously this is the successor path. With FD of 1, it can reach to N. Likewise, for B, you can see 1 plus 1. So B, the feasible distance, actually the successor. So this is the successor path. So the feasible distance is 2. For C, again, 1 plus 1, you can see the successor via A, and the feasible distance is 2. Now, for D, you will see the dual algorithm will come into the picture. So for D, to reach to N, what are the parameters? Means what EIGRP dual algorithm will provide? The point here with the dual algorithm is this, that it should be loop free. So either you can use path in this way. So this may be path number 1, or this may be path number 2. Either we are going 1, 2, or 2, 1, whatever a successor and feasible successor we have, it should be loop free, because EIGRP dual algorithm, they are maintaining loop free path. Okay, so for example, in this case, suppose B is my successor. So if B is my successor, that means that via C, I have my feasible successor or backup path. Now it up to router number D that from C it got the update, or from B it got the update, means from the neighbor who has sent the update first in case of equal cost, correct? So here you can see that you have the equal cost. Now in case of equal cost, it depends that what is the frequency, how sooner we get the update from my neighbors. So that will become the successor, and other path will become the feasible successor or the backup. Okay, so that's one very important thing. Now let's understand the failure scenario. So suppose this is your primary path and this is your secondary path. Now, if the primary link, so a link between A and B will go down. Now, since D has primary and secondary, that means D has the successor and feasible successor. So at that time, route computation will not happen. Okay, so routers, they will not do the route computation, convergence will not happen, the CPU processor of devices will not get utilized. Now it will get utilized, so route computation will occur with respect to dual algorithm and with respect to C. Now think with respect to C. Now if the link between A and C will go down, for D there is no problem because I have my primary path and I have my successor, I have my primary path, there is no problem. But with respect to C, what happened? For C to reach to N, he loses his primary path and he don't have any feasible successor or backup. So in that case, he will go and send the query to D. He will tell D, I want to form, I want my successor, I want my new path. So the new competition, so dual algorithm will come into the picture. So as per the neighbor exchange, as per the topology exchange, C will figure out how to reach to the N, and this time the route competition will happen. Okay. So clearly you understand which case you have route competition, which case you don't have route competition. Okay, great. Now these terms we have discussed earlier. So with respect to A, who will be the RD? We know that RD, that is coming from your neighbor. So from your neighbor cost B, C, and D, these costs will become your RDs, correct? And in the previous section, I told you that the formula for feasible distance is least of the compute distance. This thing we have discussed earlier. So that means 10 plus 10, you will find 10 plus 10 is 20, and that will be the least of the compute distance. So here you have the compute distance. Let me go to the next slide. So here you can see that compute distance is 20, here it is 25, here it is 45. So that means that this is your primary path or successor. Now, as per the rule, how we are choosing the backup path or the feasible successor. So we know that formula again. So here you can see you have 10. So that means your FD should be greater than RD. Correct. So in that case, if FD is greater than RD, that will become your feasible successor. But the point here is this, and that's important point here is this, that while choosing the feasible successor, the dual algorithm, they are marking the loop-free feasible successor as well. So what does it mean? It means that you have your primary path, correct? And then you have your secondary path, correct? Now, that's the key here with the dual algorithm. So now you can see that 30. 30 is greater than the FT because FT is 10 plus 10, 20. So now what EIGRP dual algorithm will do, that they will put this particular path, they will mark this as a looped path. They will not mark this as a loop free path. So they will put some sort of marker there, and that's the algorithm. So the algorithm may mark some loop free path as possible loop. So it may be, and that's the key here. So it may be loop free. This may be loop free path, but dual algorithm, this will mark this as a looped path. Okay, and maybe there may be some internal loop or something. So that's why. So it is not out of suspicion that this particular path is loop free. So you have your primary path, loop free. You have your secondary path, loop free. Primary path, we know the formula for primary path is feasible distance is the least of the compute distance. And for the secondary path, the formula is that feasible distance should be greater than reported distance. Now, if feasible distance is less than reported distance, so dual algorithm will mark that particular path as a loop path. Okay, so this is the way that dual algorithm is working. I hope you understood all the points here. In this section, we are going to discuss about EIGRP convergence process, and then we will go and check the stuck in active case. Upcoming section, we are going to follow the path. In case we have a stuck in active, what are the things that we should do? Let's discuss about the convergence process. At this point of time, we know that inside EIGRP, we have primary path, we have backup path. That means we know about the successor, we know about the feasible successor. So suppose if your compute distance, and here you can see that your compute distance, so your FT, feasible distance or your successor distance will be least of the compute distance, correct? So here you can see 10 plus 10, 20, and this 20 is the least. Now this 20 become your primary path. So this is my primary path, and we know that to become feasible successor, your reported distance. So this is the RD. RD should be less than FT. So this is my secondary path. So these things we have discussed earlier. Now what will happen if you have any problem issue with the primary path? So that means if primary path will fail, still we have the backup path inside the topology database, and the convergence will become within milliseconds. So there is no problem with the failover. If the primary will go down, this will come immediately. No problem at all. Now the convergence time will occur. It will happen when your primary and your backup or secondary path all went down. Now at this time point of time, what will happen that A will go and do the query. He will go and do the query to D, and D has to send the reply. So suppose if you have network behind E, suppose you are looking for 1110, that's the A. A is looking for 1110, and both the link you can see this is down, this is down. So he will send query to D. He will ask D, do you know this network? Do you have this particular network I'm looking for? Then D obviously will do the query to their peering devices. Once D will get that information, he will go and send the reply. And we know all these query and reply packages, they have the acknowledgement. But here you can see the problem. The problem here is this: suppose if D don't know how to reach to 110, there the stuck inactive and all those things that we are going to discuss will come into the picture. But suppose if D knows this, he will respond to A, and this process may take some time. Okay, if D knows, obviously you know that query update, he will go and install that uh, table, that route inside the table, and this will become the primary path or the successor. So it will take some time. Let us continue the previous section. Here you can see the diagram. I have router number A, and suppose he is missing one route 10.10.10.0. Now for that route, he will send the query to B, and suppose if B has, obviously we will respond. If we do not have, then B will forward that query to C, and then if C has, then C will respond, then B will respond, and then A will go and install that route inside the topology table and the routing table. Now, by any chance, suppose if C do not know about that particular route, then what will happen? A will send the query to B, and then B will send the query to C as well, while A is waiting for B respond. And suppose if B is not responding, then after 90 seconds, A is going to send the SIA query. That means, what does it mean? It will tell that the stuck in active bit has been enabled. My route is already active and now it is stuck. See, there are two things. Route may become active. That's quite normal in a network. But if routes, they are becoming or they are getting stuck, that is the problem. Now, if a route becomes stuck, that means there may be issues in a network. And then we have to go and figure out the stuck case. Active is still okay because active means some flapping, some interface issue, something is there. But if it is in a stuck phase, that means need to be get troubleshooted. And there are so many different scenarios, use cases are there for a stuck in active. Maybe some internal bugs as well with Cisco that you have to go and reboot the routers in between the paths. So those things are also there. Okay, great. So what is happening that after 90 seconds or 1.5 minute, router A will send the stuck in active query to router B. Suppose if B is not responding, then again this particular timer will get reset. And there are certain messages. I think router will send 6 messages until it will go and mark that that particular route is unreachable, or it will delete from its active state. Okay, so there are chances that suppose if you are looking for route, if router A is looking for this particular subnet and he is not getting it, that means after a certain period of time, it will mark this as a unreachable and it will remove from its database. Okay, now how we can go and do the troubleshooting for this case. So what we can do, there is one nice command, show IP EIGRP topology active, but this command is useful when you have the issue. Suppose if issue is gone, this command is not that useful. So suppose if you have issue related to active and stuck in active states, you can go and run this command, because this command will clearly tell you that you are looking for this particular route which is active 2110, and then I am querying to my neighbor. You can see 101112, and it's slow to respond. You are waiting for the response from B. Now what B will do, obviously B will go and send this query message to C. So while doing the troubleshooting, you can go and check here, you can go and check at the B, you can go and check at the C, at the D. Everywhere you can go and check show IP EIGRP topology active. Correct. Now you are following the path, you'll find that at the C also you can go and check that it is active, active since, and slow to respond. But suppose if you go and check on the D, and in D you will not find any active route, no messages related to that, then what will happen? Correct. That means that you have issue in between C and D. There may be some other issue, maybe a processing issue, maybe some unreachability issue. There are a lot of issues. So you can go and troubleshoot to this culprit device. That's the router number C, which is not responding. If you go and check show IP EIGRP neighbor, you'll find that queue count is 1. But again, this is one of the use case. There may be different issues, and let me go and show you. I have a list of issues. So maybe bad or congested link, maybe query range is too long, maybe excessive redundancy, overload, high CPU, router memory issue, software defects. Sometimes there are some software defects, some bugs are there. So these issues may be there. Okay, so I hope at this point of time you understood about the stuck in active, how we can chase the stuck in active states, how we can go and try to troubleshoot, figure out this issue, troubleshoot, and get the resolution. All right, so let's stop here. Now we are going to discuss the theory of load balancing, stub areas, and authentication lab will do in the upcoming section that we have already discussed. EIGRP is a protocol that can do unequal cost equal load balancing. So what does it mean? It means that if you have feasible successor, if you have successor and feasible successor, or vice versa, so in that case, one is your primary link, or one is your primary path, one is your backup, but still with help of variance, we can make both as an active link. So that means that we know that successor only get installed in routing table. But if you use the variance command, both the successor and backup successors, or the feasible successor or backup paths, those things will get installed in routing table, and you will get, although you have the unequal path. So for example, you can see these two paths, still you will see that those things will be installed in routing table. So you have the successor and you have the feasible successor, that's your backup, but still if you send 4 packets, 2 will go via this, 2 will go via this. just an example. The devices, they are not doing packet-based load balancing, but it's something called flow-based load balancing. So what's the command? Variance. We'll see that how much variance we can use. We can use up to 128. We'll see that in the lab section. Maximum path, by default it will be 4. We'll see that how much maximum path load balance it can do. Maximum it will be 6, but in higher version of operating system it may be more. By default it will be 4. Next topic we have a stub. Now we have discussed this earlier that suppose if I lose my successor and feasible successor, so at that time I will send the query packet, and query packet will get propagated until unless we get the reply. Suppose if I get the reply within 3 minutes, that's okay. Otherwise this process is known as a stuck inactive. Now to mitigate or to overcome from this, that already I know that network is not after this particular hop or router, I can make that spoke router as a stub. So that means that I am sending a query packet, but you will simply reply no. You don't have your what you are looking for from this direction or from this route or from this gateway. So that the query will get answered that this is the stub. All right, what's the command? We have the command. We should go to the eigrp process. We can go and run this command eigrp stub, and then we have 4 options. Receive only, that will not share the update with neighbor. We have connected, static, and summary options. Connected means advertise connected routes. Static means router will only advertise the static route. Summary means router will advertise only summary route. Okay, so these options we have with the stub. Then we have some verification command. We have seen this show IP eigrp neighbor. Then we have seen show IP eigrp topology. You can check who is the successor, feasible successor, FT and AD, those values we can check. Show IP eigrp traffic, already we have seen. Show interface, and you can go and check the interface, what is the delay, what is the bandwidth, reliability, load, etc. Show IP protocols we haven't checked so far, so we'll run this in the lab. Show IP protocol will tell you detail about the protocol. It's a very useful command. It is giving the detail structure or detailing about that particular protocol. Show IP route, we can check the routing table. Show IP route eigrp if you want to filter it. And then finally we have some debug commands such as debug eigrp neighbor, packet route, and summary. Remember, do not run this debug command until unless you have the maintenance window. All right, so what we can do now from this point of time, I can go and log into the lab. We can continue our lab because we have to run or we have to verify few of the things one by one. Load balancing a stub, and then we have to do the authentication lab. All right, so we are inside the lab section so far. We have ran that eigrp once over 101, and let me quickly see that if we have done over 102. 102 we haven't run, so let's go and do that. What is the network we have? We have 3 and 4. So I can go here and router eigrp 10, no auto summary, network 10.1.4.0, and then the wildcard. Then other network we have 3.0, so I can go and do that. We have 3.0, and then we have network 102, 102, 102, 102, 0000. Okay, so here also I can see that the protocol eigrp protocol is not coming up. Let me quickly go and check the interface. Maybe the IPs assigned are not correct. So we have 4 and 3. That's correct. Let me quickly check where it is connected. So it is connected 0/0, and 1/2 as per the diagram here. You can see they should go to 101, and seems this 0/0 may be passive interface that we have done. So I can go here and you can see the usefulness of passive interface. So I can go and check the configuration first. Router EIGRP10, I should do no passive interface for E0/0, and let's see. So now here you can see that the protocol is running. Great. From this direction it's okay. Let's quickly check 10/1. So I can go to 105 and I can check here the EIGRP protocol. Do we are running the network command or not? So I can go here and check section EIGRP. We have 10, 1, 2 and 3. Is it correct? So we have 10, 1, 10, 2, 10, 1, 3. That's correct. Let me go and quickly check E 10/1. So run interface E10/1, and we have wrong IP. So E10/1 IP address should be 10.1.3.105 and then 255.255.255.0. Alright, so now we can see that it is working correct. Now if I go and check show IP route EIGRP, so here you can see that you have the loopback 1, 3, 5. So we have the loopback 105, 101, 103. All these we are getting. Finally, let's quickly go here to router 1 and check do we have the configuration for the EIGRP. We don't have, and we have some configuration related to summary as well that I actually don't need. So I can go to 00 and I can remove this command. Let's do router EIGRP10, no auto summary, network 10.1.1.0, and then we have one loopback. That loopback is 0000. Now if I go to any of this switch, say for example 103 also, I should get all the loopback. So let us continue and perform the lab related to authentication, and then we have the unequal cost equal load balancing, and then we'll see that what is the command for the stub as well. So let's start this. We have the topology. Here you can see I'm going to enable the authentication in between R1 and switch 105. The common interface is E0/0. So how we are going to do, first of all, you need to create the keychain. Say for example, the name is CCNP in caps, just to refer this is the name. Then key I can give one, and then I can go and give the key string, say CCNP and then key. Okay, great. Then we have to go to the interface E0/0, and then we have the keyword called IP authentication. I should give the mode as EIGRP10 and MD5. So we have actually two commands. One is IP authentication, and at the moment I have executed this command. You can see this neighbor relationship is down. Then we have the keychain option. keychain EIGRP, and then the name of the key chain, that is the CCNP. Okay, that's it. So these are the commands we need to run in order to enable the authentication. Now the same copy paste I can do to this side, and you can see this neighbor is down. I can go and create the keychain first. Then I can go to the interface, and then over the interface also we can go and run this command. So let's do this. Over the interface I have these authentication command. We can go and enable this. Now we'll see that the neighbor will converge, and now I have the neighbor relationship with the router 1, that is 10.1.1.1.0. Just now it came back up 10 seconds back. Alright, so this is the way that we can do the authentication. Next we have the variance. So let's try to understand the unequal cost equal load balancing. Now here you can see that I can go and reach via this path to R1, and then I have the other path as well. So let's try to check the loop back that we have here, that is nothing but 1.1.1.1. So how many path we have to reach to 1.1.1.1 from switch 101. So if I go to switch number 101, and if we go and check show IP route for 11111, and I should give the network. So 11111, here you can see that I have only one path to reach there via E1/2. And if we go and check show IP EIGRP topology, and then if we go and check 1111/32, so inside topology it is telling that you have 2.105 and 4.102. So here you can see that it can go via 102 this way, and it can go via 105 this way. Obviously the metric value that you can see here, the FT and AD values, those are different, but you have two paths. Now, is it a successor? So we know that who is the successor. Successor is this, because obviously it has lower FT. Here you can see 435200. And if you go and check this output in this manner, just to see that to reach 11111, I have only one successor. Okay, although we have two paths to reach there. So in this case, this will be direct like this via 105. Other one will be via 102, and then 105, and then R1. So what we can do now, I just wanted to add up the value for uh, two different paths. So suppose if I want to decrement this, first of all, let's try to understand, can I do some sort of traffic engineering that traffic will go via this direction rather than directly? Let's try. So that means I have a bandwidth here defined and here defined, and that means that I have to increase the bandwidth at 2 point over switch 101 and then switch 102, correct? Because all the links have equal bandwidth. So if we go and check the bandwidth for 0/0, show interface is 0/0, here you can see that it has bandwidth this. Now I should increase the bandwidth So 1, 2, 3, 4. What I'll do, I'll go to interface E0/0. Bandwidth is, for example, 5. 1, 2, 3, 4. Now let's see the show IP route for 1111, how it is going. So now we can see that still it is going via 105. That is still it is going directly. Now next what I will do, I'll go to 102 and I'll change the bandwidth of E1/2. So I am here, E1/2, bandwidth is 1, 2, 3, 4. If I go here and check, so what we are doing here, that we are trying to forcing the bandwidth so it will change its metric value, and so we can see that show IP Eigrp topology, that it is going via E1/2 rather than it is going via E0/0. And if we go and check topology for 1111/32, now if you check the composite metric here and composite metric here, still we don't have much change in the composite metric. Obviously the reason here is that you are changing the metric here and you are changing the metric value here. We should change here also, that is E0/0, and the bandwidth is, so we are just forcing the bandwidth. Now if we go and check, and still we can see that it is preferring this way. So IP route, so there is no change while we have changed the metric. For 1111, it is still going via the directly connected path. Okay, still it is going via this direction, although we try to change the calculation because still it may be less than what we are getting from tooling. So for example, 102 you can see what's the metric value here, 2048000, and then if you go and check the metric value from here, so if I go and check show IP route to reach to 1111, so switch number 2 to reach to router number 1, here you can see this is the metric, and if you go here, so seems the metrics are very much same. So how these guys are reaching is that they are coming to this this point, and then it is getting advertised to these directions, correct? All right, so here you can see that in this case, if you want to do traffic engineering, it's very difficult to do the traffic engineering. But one thing that we can do here is unequal cost, equal load balancing, correct? So if we have successor and if we have feasible successor, then it will be very easy to do it. Now in this case, I don't have any feasible successor. So IP Eigrp topology. So I can see here that I have only successor. I don't have any feasible successor. If I have feasible successor, then it's easy to do, but still I can go and use the router eigrp 10 and then the command say we have variance. I'll give the worst case, that is 128. And then if you go and check show IP route, specifically I want to see for uh, one of the route, but here I can see that 105 now have two different having equal cost multipathing, although you can see the metric value is different. So if I go here to the topology, you can see that from uh, switch 101 to reach to 105, and obviously you have one loop back. I have two paths, this path and this path, these two paths. You can see their metric value is different. One is 2300, one is 409, and how we are doing the calculation actually, that's 230 and 409. You have to simply divide it, and you'll find it's almost double. So the difference is of double. So what I'm telling here is that when you are using the eigrp value, we have given the variance of 128, that's the boss. You can give 3 also. And then if you go and check the route, you'll find that they are doing the unequal cost equal load balancing. And again, if I go and check show IP route, or maybe show IP eigrp topology for this guy, and should do this with 32. So now here you can see that you have this path that is going via directly to the switch and then loop back, and then it is going via the other switch, and then here you can see the metric value, this and this. The difference is almost double. Okay, so now I can see this, and if I go and check show IP eigrp topology, so here in the topology you can see that it is 105. So here you can see that you have two successor. So at this point of time it is showing two successor. Obviously if you have successor, then that will be installed in the routing table, because we have done so many changes in the bandwidth also. So that may be one of the reason the metric values get very much balanced. So let me quickly go and revert back the change. So I'll go to 102 and I'll change the bandwidth for E12 and E00. So let's do this. 00 bandwidth is 1234, E1/2, 1/2. The bandwidth is, because again if you change the bandwidth, you'll go and see the values will get changed. So for 105 now you can see that you have only one successor, although we have used the command called variance. So if I go ahead and check show IP route for 105 there you can see that you have only one path. Okay, so this is the use of the changing the metric value with help of bandwidth, although we know that we can change with a delay as well, but I'm not showing here. We can change with the bandwidth, and then we can play around with the variance command. Finally, we have one use case related to stub. So suppose in this case, if I got some issue, and if something will happen with my destination network, somehow if I am not able to get my destination network, so what will happen? So in this case, uh, suppose if 105 is the hub, so this guy here is the hub and these are the spokes. So you can go to the spoke and simply you can enable the command called stub. So suppose if this link will go down, for example, just in case of example, and because this is the stub, so the query will not processed, and simply the stub will respond to the hub that, oh, you can't go beyond me, I don't have any network that you're looking for. So in this case, what we can go do that we can directly go here and we can go to router EIGRP and we can check the stub command. So if we have EIGRP and stub, now you can see that you have connected, leak map, receive only, static, summary. So we can give connected and summary. Now you can see that it reran the algorithm. So now this become the stub, and the theoretical aspect of this we have already discussed. All right, so let's stop here. Let us understand some more terminology and theory for EIGRP, and likewise we are going to continue our lab as well. So the next topic we have related to passive interface, auto summarization, and authentication features. Let's see here in the slides, we'll go step by step. Now, first of all, when you're doing the baseline configuration that we have already done, go and enable the EIGRP process with autonomous system, and then we have option to advertise the network. Now, we can go and add the wildcard bit as well, so we can get the specific network advertisement. Once we do up to this point of time, obviously we know that the hello packets will start exchange and then they will form the neighbor relationship. First of all, we have the neighbor relationship or neighbor table, then topology table, and then finally the routing table. All these things we are going to see in the upcoming lab as well. Then suppose if you don't want to form the EIGRP neighbor relationship like we have done in OSPF earlier, so then I can go to that particular interface and I can make that interface as a passive interface. Standard format is that you deny all the interfaces like passive interface default, and then selectively you can go and add the interfaces who want to do the EIGRP hello exchange or EIGRP packet exchange. So for that we have the passive interface default, and then we can go and give no passive interface and then the interface name. Now again, we have learned this in OSPF that how we are going to do the summarization. In OSPF, we have summarization, or we can do summarization over area. So we have used that command. I have shown you that how that command work, or how we can use that command, and then we can do the summarization for ASBR as well. So we can do the summarization for ABR and ASBR. Here in EIGRP, this summarization is a bit easy. So first of all, in the previous section, in the lab section, we have used the auto summarization, because if you do not do the auto summarization, so in that case, what will happen that it can be converted to their class boundary. So for example, if you have network 10.100/16, if you do not use the auto summarization, like no auto summarization feature, then it will think that his network is 10.0.0/8 because uh, 10 is belonging to class A whose subnet mask is 255.0.0.0. So like that, we need to use this keyword like no auto summary. You have to use this, and then coming to the manual summarization. Now the same thing that we have discussed in case of OSPF, you have to go to the interface and then summary address EIGRP, the autonomous system, and what you want to summarize. So you can do the summarization. I'm going to cover this in the lab section. We'll create some different type of network, and then we'll do the summarization, and then we'll send to the devices. Now when we do the manual summarization, at that time the AD value is 5. We know that the internal AD value is 90, that EIGRP AD value is 90, but for the summarization, our AD value is 5. Now we have one note here that as with auto summarization, the router performing manual summarization will add the summary route to its routing table with a next hop of null interfaces 0. So we know that you're doing no auto summary. See, that's the combination. Do the no auto summary. You're not doing the summary automatically, and then you are doing the manual summarization, and that's the reason we have this AD distance as 5. Obviously, that is more than the internal distance. Okay, so do not mix with auto summarization and use this practice, no auto summary, and then the manual summarization. Then finally, in this section, we have the authentication. First of all, we have to create the authentication key. So here you can see that key chain. Define the key 1, 2, 3, 4, 5, etc. Then key string, define the password. And then over the interface, we have to go and apply it like IP authentication keychain, autonomous system, and then key. If the authentication or the password will match for both the peer interfaces, then only they will start exchanging the EIGRP hellos. Okay, so these are the topics that I'm going to cover. Let me open the lab section and let me show you whatever we have discussed here and what are the things that we have in the leftover in the previous section as well. As per our lab topology, what we have done that we have enabled EIGRP over 101 and 103. So now if I go here and I can show you this, show IP EIGRP neighbor, show IP EIGRP topology, and show IP EIGRP. Better I do show IP route EIGRP. That's the routing table. So whoever is your feasible successor, that you will see in the routing table as well. So here you can see that what is the network that I am learning here, and that's why it is there. Rest all the network actually is connected. So you can see all are connected routes, and then finally I'm learning one of the loopback, so that's why it is coming inside this routing table. We should check all these things first of all. Then if you want to check the packets, so we have the show IP EIGRP, and here you can see the traffic. Here you can see that what type of packets you have: hellos, update, query, replies, acts, stuck in active. So all those packets we have. With this command, we can go and check the packets as well. Okay, and then how we can go and change the metric values, so that we have discussed in the previous section. I can go to EIGRP and then you have command metric weights, and then you can see that say for example type of service K1, then K2 for example, then K3, K4, K5. So like that we can go and put all these values. I'll not put this value, and just showing you that you can go and check these values. Now let me go here and let me show you show IP route EIGRP. So here you can see that you have your AD value, you have your metric value. Now if you go to the interface E0/2 and 0/2 where it is, so we are here, that is going to switch 103, and I have this option that I can go and change the bandwidth. So if I go and change the bandwidth to 5000, and if I check show run interface E0/2, show interface E0/2, here you can see this bandwidth is 5000, and here it is 5000. Now if you go and check the metric value, because we know that the metric value will get changed, so now it become this. Initially it was, so now it is 1 2 3 4 5 6 6 digit, because initially I think that was 10000, I think 1 and 4 times 0 the bandwidth. Now if I go up and if I can show you the bandwidth that was before change, so 1 2 3 4 5 6 409 600, that is increase, because this increment is bandwidth and metric are inversely proportional. So if this number is increasing, that means the bandwidth is decreasing. What I'm telling you, that if you go to interface E0/2 and if you give the bandwidth, say for example one move 0, so if this will increase, this will decrease, correct? Do show IP EIGRP or do show IP route EIGRP. So now you can see that this is decreasing. So if you increase the bandwidth, your metric will decrease and that will become more and more preferable. All right, so these things are related to the previous section. Whatever things we have studied now, that let's cover that. So first of all, we have a study about the passive interface. If I go here and let me do one thing, I'll enable the EIGRP over this devices as well, 101 and 105. So let me quickly go to 105 and enable the EIGRP. And before that, let me check what is there inside 101, what interfaces we have. So we have three interfaces, that's correct. And then we'll go here to 105 and we are going to add the interfaces. So we have 10120, 10130 and 1. So 1, 2 and 3. All right. So let's do this. Say router EIGRP 10, no auto summary network 10.1.1.0. Then we have 2 and 3, correct? And then we have one loopback as well. So 2, and then we have 3, and then we have network related to 105, 105, 105, 105, 00000255. All right. So there the network we have. Now since it is not coming up, that means something is wrong related to interface is down or something that we need to check. 10120 E11 and E10/0. So if I go and check to show run interface, say do show run interface E10/0, I can see that the interface is correctly defined. Then I'll go and check to E1/2, E1/1012, and if I go and check to show run or show run section EIGRP, should have routing for that. So I can see 10120 12.105. Yep. Some issue seems to be related to connectivity or maybe interface that we need to figure out. So here you can see the issue. My interface should have correct IP address. So IP address is 10.112.105, and you can see 2.1 and 1.2, how minor mistake that was, but again we should give the correct IPs, and now it is up and running. I can go and check show IP EIGRP topology, or I can go and check show IP route EIGRP because I'm interested in that. So here you can see that it is getting the loopback 103 and it is getting the loopback 101. That's why I've given the loopback addresses. So that means I have the reachability. Now if I go to 101, because he has two neighbor at this point of time, So IP EIGRP neighbor, one of the neighbor I want to make passive interface. So for that, I can go to router EIGRP10, say passive interface default. That means everything is passive. Then we can do no passive interface E, say for example 1/2, and then I can go and do no passive interface for E 0/2. So this is the use of passive interface as well. Okay. Now what we can do next, that we have the summarization option as well. So for that, I can go to, let me open this diagram. I can go to 103 and I can create some loopback addresses here. So for example, 7 or maybe 103, anything. So let me go and create some of the loopback. So I'll go to 103 and I will create few loopbacks, say interface loopback 101, IP address, say for example 2.2.2.1, then interface loopback 102, IP address 2.2.2.2, and then interface loopback 3, or maybe anything, IP address 2.2.2.3, 255.255.255, interface loopback 4, IP address 2.2.2.4. Like that, I can go and create some of the loopback I want to do the summarization for. Then I can go to router EIGRP10. I can do the advertisement, say network 2.2.2.2.0.0.0.7. Do show IP interface brief if you want to check your loopback. So 3, 4, 101, 102, etc. But network is 1, 2, 3, 4. Now if I can go and check these routes here, show IP routes for EIGRP, do I am getting the loopback. So here you can see that we are getting four network. Rather, I want to want one advertisement. So what I can do here, that I can go to the interface. So let me check what interface we have. Brief, we have interface inside 103. So let me show you this diagram here. So we can go to 103 interface 0/0 and we can do the summarization. Okay, so interface is 0/0 IP, and then the summary address EIGRP 10, and then we can do the summarization. So 2.2.2.0, and then we can give the mask, say 255.255.248. All right. Then if I go here to 105, you can see the AD value is 90, 90, 90. 105 is getting this single advertisement, that's okay. And if I go to, I'll cover that. So now you can see that this, once you do the summarization, the EIGRP algorithm will rerun, it resynced, and it has sent the summary. Now if I go to 102, and here if I go and check, oops, we'll wait, and let's see the final command. So what we have, show run section EIGRP, and we have done this summary. Great. So we'll go to the 102, and in 102 also I'll go and verify that what advertisement exactly I'm getting here. So we'll go here and check show IP route EIGRP. Where we are, I should go to 101 as per the diagram. We haven't done any configuration for 102. So show IP route EIGRP, and we are getting this advertisement. And if I go to 103, who is the originator? Show IP route EIGRP. It is sending the summary to the null, and then it is getting advertised to all the devices, correct? In this section and upcoming few videos, we are going to learn more about EIGRP troubleshooting, and I have one lab as well. Inside that lab, we'll go and do the troubleshooting related to EIGRP. So here you can see the lab. In this lab, there are two domains, EIGRP and OSPF. You can see the IP schema. So suppose if I have router 1 and if I have router 2, so I have taken the IP subnet like 10.1.router1 router 2 is just the name of the router. So in between 1 and 2 we have 12.0 network. In between 2 and 3 we have 23.0 network. In between 3 5 router 3 and router 5 we have a network 35.0, and everything will be a start with 10.1. So 10.1.x.x is the network I'm using. Now we will go first of all and see the baseline configuration in this particular lab. So at least the first portion where we have the EIGRP configured. So in this EIGRP with respect to router number 1, 2, 3, and 4, we'll go and verify the configuration related to EIGRP. So I have done baseline configuration related to IP addresses over the interface plus EIGRP routing configuration. Now this router here, router 6, actually it is working as a client network. He is a client, because then we'll go and examine the path, traffic path that will be optimal. So if you suppose at this point of time, if we go and do the redistribution, there are chances that to reach to certain destination, the router, so this client may take some suboptimal path, or it will not go via as per intended, or as the as per the lowest hop count. It may take longer route to reach the destination. We'll see that. There's a troubleshooting that we have to do in the upcoming section. Okay, so to start with, what are the things we want to do while doing the troubleshooting? First of all, we should have the proper network topology diagram. We should know the network first. Then we should go and do the neighbor adjacency troubleshooting. We should check the best path selection. If it is not doing best path selection, some redistribution issue, some AD issue, we should check that. Then do we have primary backup paths? If it is there, then failover scenarios related to primary and backup, we should know that. And if some features related to EIGRP that is causing issue, we should check all these things. Good to know that we should have good understanding of that particular protocol and the topology, and then we can go and use different type of tools. So what type of tools we have? See, we have the tools, we have the troubleshooting tools, show command, we have log commands, event history, debug commands, and packet capture. These are our tool belt. Correct. So first of all, with the show command, you'll come to know. So there are always some basic show commands like show IP, EIGRP neighbors, interfaces, topology table, routing table. With show command, we should check all these information, because we should be knowing that what exact issue we have in the network. Then you should go and check the log files. We can go and check the event history if required. Now, if we go and enable the debug, that is in T-shape. So if possible, use it with caution, use it with ACLs, filters, and then apply the debug command. Because if you go and apply the debug command, there are chances it will break down the device. And then packet capture. Even packet capture and debug commands, we should use with caution while doing the debugs, while doing the packet capture. Best practice is that always try to use ACL, access control list associated with these informations, these tools. How we can go and verify? So always use the show command. We have various show commands. We can go and check the log commands. We can go and check the event history command. So some top commands: show IP or IPv6 EIGRP neighbors, EIGRP interfaces, and detail options are there, the events, and then show logging. And then you can go and use the debug, but use it with care. Okay, we can go and check the log. Even we can collect the log somewhere and we can analyze the log. Like that, we can go and collect the logs and then we can analyze the logs. Okay, so let me quickly log into the lab device where we have R1, R2, R3, just to show you that what basic commands we have. Router 1 is actually working as a gateway for router number 6. Here you can see that if I go and check show IP into brief, if we have issue with the client and he's not able to use the specific applications, so that also you can go and check the best path. So is that client using best path to reach the destination, etc. Okay. Show IP. Let me show you the configuration first in router number 1. So I can go and do show run section EIGRP, just to see the EIGRP related commands, and you can see that we are using the default metric here. The command, you can see redistribute connected. If you want to advertise your redistributed network, you can use that. Now here, what I can do, I can show you show IP EIGRP neighbors, just to start with. Then you can go and check show IP EIGRP interfaces. Then you can go and check show IP EIGRP. Oops. Let's see what options we have. So you can go and check always the interface. You can go and check the neighbors, and one of the top command is the topology. And with the topology, and these things we have discussed earlier as well. The topology can go and give certain IP subnet as well, that exactly what topology you are looking for. And active is also one command that we have discussed earlier as well. The topology will give you complete topology table. If you have one router where you have multiple redistributions and all, so there you can get much more view related to the network. Okay, so these are the top commands that you can go and check in the first instance. You can go and check show log. You can see the log. You can go and enable the debugs as well with cautions. And let me go here. So I can go and use debug EIGRP packets. And at the moment you'll go and enable, you will see so many messages will come. Okay. And you can see that not only debug packets, but you can debug transmit as well. All right, so these are the basic command. What we'll do in next section, we'll go and check the trouble tickets related to our lab setting. Now we have trouble ticket related to EIGRP. In this particular trouble ticket, let me explain that what's the issue and what we want to sort out. So we have the topology, and we have seen this earlier. In this particular topology, we have one host whose IP address is 10.1.16.100, and we'll go and verify the host IP. Now what is happening here, that R4 here wants to reach to this particular IP. Let me draw the path here. So R4, router 4 wants to reach to this IP, but what is happening due to redistribution problem, due to AD issue, administrative distance issue, what is happening that R4 to reach to that destination is taking longer path. It is termed as a suboptimal path. Why? Because EIGRP having external AD value 170 for this particular route, and OSPF having AD value of 110. So what is happening when router number 4 is getting this network? He has two options. He can get this network via a router number 2, is this advertisement, or he can get the network when the EIGRP will go to OSPF, and then OSPF will redistribute and send it to router 4. Due to this AD problem, this particular router is installing the route via OSPF, and that is not the shortest path. That is actually the longest route. Okay, so now we have to go and fix this issue, so that the actual path that router number 4 will take to reach this particular IP or host via the first one, not the second one. So first of all, we'll go and verify this issue, and then we'll go and correct it. Let me quickly go to the lab devices that we have. And here we have the lab. All right. So here in this lab, if you go and check the host IP, that is actually in router number 6. And what I have done, I have made this as a host. That means so routing is disabled on this particular router. He has this particular IP whose gateway is 10.1.16.1. Now, if we go here to router number 4, and if you go and check the route related to that particular route, that is 10.1.16.0, you can see that it is learning with respect to OSPF E2, correct? Learning from the interface that is 45.4, and 45.4 is something here. So let me clean this stuff here, and I can see that 45.4 is there. So he's learning the route in this direction. He should not learn in this direction. He should learn in this direction, via this direction. Great. So let's go and correct this. And meanwhile, I will copy the running configuration and share so you can see the configuration. One important configuration that we should check here is the redistribution. So I want to show you the redistribution configuration over router number 3, because router number 3 and router number 4, they are in both the domains, correct? So you can see here in the back, router number 3 and router number 4, they are belonging to both EIGRP. So you can see EIGRP and OSPF. Although in router number 3, we are going to OSPF and we are redistributing the EIGRP routes, correct? And router number 3, we are doing the redistribution, correct? And then it is router number 4 is learning via R5. So if I go here to router number 4, and if you go check the configuration, you'll find here I'm not doing any redistribution, but we know that we can do the mutual two-way redistribution in case we need high availability. So if one link will go down, one side will go down, still it can learn the routes from other side as well. Okay, so one solution here is this, that we can go and shut down this particular link, correct? This link is what? This is on router number 4, gig is 0/2. So if I am here in router number 4, and I can go and shut down interface gig is 0/2 is the interface actually. And let's shut down this interface. And now if you go and check the route, do show IP route, if you do, you will see that now it will start learning the route with respect to EIGRPC, but you can see the AD value. The AD value now he is learning is 170, that is way more than OSPF 110. And thus that's the reason that you can see that he is learning that if we go and do shut down the interface, that is not a good solution, because you are shutting down one of the interface, correct? So what we can do here, we can do the no shut. Let's revert back the network, and let's check the route again. You will see now it will again start learning from OSPF. That is not the optimal path. So what we can do here, that we can go to router EIGRP1. Remember, one very important thing here is this, that administrative distance, they are locally significant. Okay, so now here we can go and we can use the distance command, and then you can give the internal AD distance, that's 90, and then external, instead of 170, I can go and give less than 110. So I can go and give anything less than 110, maybe 109 will also work fine. Enter. Now once we do this, and if you go and check show IP route, you'll see that it will again start learning with respect to EIGRP. So here you can see that EIGRP got flapped. See, reconvergence is happening, and now it formed the new neighbor relationship. And now if you go and check the routing, you can see that he is learning the route in the correct path with a lower AD, lower than 110. So you can see clearly this 99. So now the route is learning via the correct path in this direction. So this is the troubleshooting, and in a bigger network, there may be chances to troubleshoot this. You have to find out the issue, so it will take much longer time to find out the issue, and then you need some change approval to do the configuration related change. Okay, so it may take good amount of time while you are doing troubleshooting in the production network. All right, so let's just stop here.
Thanks everyone for enrolling this course. In this course, you will learn all the technologies related to CCI Enterprise. But in case you are looking and you are preparing for your lab exam, please feel free to contact. We are running some sort of 100% guarantee program to make you pass. I will provide you the lab, resources, everything. If you want to know more about this offer, you can go and email to this particular address. Anyways, in this course, you are going to learn all the technologies. This will be very useful course to you. But in case you are planning to write your lab exam, just feel free to contact us. We'll provide you all the guidance, all lab related tips, techniques, all the passing techniques, etc. So please do not hesitate. Feel free to contact us and we will provide you and we will assure you that you pass your lab exam in first attempt. Thank you.